Okay, so
You can,
maybe
but
I should perhaps slightly clarify that I'm not going to talk much about gravitational waves. If you expect, an explanation of how they come about, but much more, since I'm an experimental physicist, how you can actually, or what people did to actually see them. Okay, so I guess if you are interested in how they come about and what mathematical formalism is necessary to come up with that, then you should get to people who work on general relativity in our department, and they will be able to explain that really nicely, hopefully, how this comes about. I give you an experimentalist's point of view, since I'm an experimental physicist, and what I try to maybe talk about this session here is how they managed to observe that event. I mean, probably all of you have heard that last year, sometime around that time, or maybe a little bit later, they announced that they have detected finally gravitational waves directly, and they called this the GW 1509-14 event, suggesting that, I mean, the actual event that happened was happening in September 2015, on 14th, I guess, and there was an effort from a lot of scientists, so a super international effort of getting a gigantic telescope, if you want, or a device working that was finally able to detect gravitational waves directly. So, maybe this works here. This is supposed to work, but it doesn't. Just trying to this now. That's sad. Anyway, I just try this one here. Okay, so the news that made it, you can, I don't know whether this works here. This is supposed to be a link to this this physical review letter paper. That was sort of like the official announcement, and that's how people in physics often announce something, not by a press release, but by having a peer-reviewed article, because you want to make sure that if you make a very strong claim, then several people have checked this before you go to the press and say, or Twitter it. These days it has become popular to Twitter about things before you think about it. But it's not a style yet in physics. So the sort of like official announcement that this has happened was this particular article. And what you see here is sort of like a characteristic plot, because in physics you always try to show things often by graphical representations. They have basically two observatories, one in Hanford in US, both sites are in US. One is in Hanford, that's in the northwest of the US, okay? And the other one is in Louisiana, it's in the southeast of the US. So there's a few thousand kilometers space between. And what they measure is a so-called strain. Okay, that's one of these properties that characterize a gravitational wave. So that sort of like changes the metric of space-time locally a tiny little bit. Okay, and that's not a lot. So I probably can't read this, but this is sort of like 10 to the minus 21. To have this sink in. Okay. It's a very, very small relative change of length measure. So they have an instrument, they actually have two instruments that measure that, and they could see at the same time in two locations that are a few thousand kilometers apart that this sort of like strain showed some funny wiggles, okay? And they were synchronous, okay? So they could figure out that they saw the same event on both remote sites. And the conclusion is, after making many checks, that this is not some fake news, I guess would be the word of the day. They confirmed that this can only be explained by a gravitational wave event, and they have a rough idea where this sort of like happened, because just out of the geometry and the time delay from seeing it on one side and the other side. So. And the conclusion was, what they wrote here, that this type of signature of gravitational waves must have been a black hole merger. Okay, so you have basically two black holes, some size, a few solar masses, okay, and they were spiraling around each other and sort of like coming closer and closer. And in this process, they sort of like they emit these gravitational waves, okay, and they come closer and closer and closer and emit more and more of their more and more energy into gravitational waves. This whole process, I think they lost about 3 solar masses, okay, times c squared in energy in gravitational waves. That's a lot, okay. These black holes, they believe, I mean, that's sort of like, you know, they don't know what happened there, but they do a simulation and try to figure out what has happened. These were sort of like, they can simulate this event with 2 black holes with mass about 30 something, yeah, roughly 2 times 30 solar masses for these black holes. And they're sort of like merging together into a single one. And in this process, they emitted these gravitational waves. Okay, so that's sort of the, still doesn't work here? Okay, oops, now this is going too fast. Okay, so gravitational waves, this is sort of like the artist's impression, if, you know, because there are no pictures of the whole thing, so you ask an artist to draw something. Maybe the easiest way to understand how gravitational waves come about, okay, without going through the full Monty of the general relativity. I don't know, maybe you have gone through this and you know much more about that than I do. But the way I like to look at it is maybe I just compare it to electromagnetic waves, because that's sort of something I believe I understand a little bit. Then, and the basic idea is, so you start out with electromagnetic waves, you have two charges, okay? And they exert a force on each other. And if you just write down this Coulomb law, then sort of like the force is just proportional to the distance or the relative position to these masses. But you know this information where the other charge is, you can by sitting on one charge, cannot travel faster than the speed of light. Okay, so there must be something that tells you if this charge moves a little bit to the side. Okay, that information cannot instantaneously go from one mass to the other mass. And what you need there is sort of like an electromagnetic field, okay, or an electromagnetic wave to carry that type of information. And you have a similar situation with Newton's law, okay. So there again, you know, it's sort of like high school physics. You basically have 2 masses, they attract each other, okay. And you know, this if you write down this law, that would be something that implies that there's an instant action. So if sort of this mass moves a little to the side, then the other mass would sort of feel a force that changes instantly. Okay? And that's not the case, because nothing can propagate faster than the speed of light. One of these insights in relativity. So and similar to the electromagnetic waves, you would need to have some mechanism that transports this information about the gravitation from this one moving mass to the other mass. Another way of looking at it is sort of accelerated charges emit electromagnetic radiation. So one of these examples you probably have seen is in the synchrotron. You know, you have an electron just going around the corner, or getting accelerated on a circular trajectory that emits light. Okay. And if you have a mass distribution, you sort of like don't have a dipole moment that changes over time, but you have because you cannot have that easily, because first of all, you have mass has only one sign, and the other reason is if you have an origin that's defined somehow in a funny way, that you can find very simple arguments that the simplest non-vanishing term of a mass distribution would be sort of like a quadrupole moment that can change in time. So this gravitational wave that runs away from something and survives over a long distance, okay, meaning that goes with 1 over r, must be a quadrupole moment of a mass distribution with these 2 masses rotating around each other, and a certain time derivative of it. If I get it right, it's probably the 4th time derivative of the quadrupole moment of this mass distribution. That sort of like causes the part of this gravitational waves that you can still see very far away. So this is sort of like a super short analogy, perhaps, how rotating masses and moving charges Now for electromagnetic fields, you do see, the way how you measure a propagating field is you measure the electric field, okay? And electric field you measure again by having a test charge and measuring the force on it, how it wiggles, for example. Okay? Just switch this off here. Okay. So then the screen does funny things. Okay. For this gravitational wave, the manifestation is not a field directly, but what you can see is that sort of like the local metric changes a little bit. Okay, and a local metric basically is also not so easy to measure. Okay, but what you actually can measure, just have this here. So a change of local metric basically gives you a ratio of the distances in one direction and another direction of a solid object, but that's also probably a bit ill-defined. So a better way of defining is you have sort of like a bunch of test masses that are in rest with respect to each other. Okay, and you try to figure out how does the distance change with respect to these reference points. Okay, so and that's sort of like that type of oscillation in this metric. So in one direction it goes a little bit larger, and the other direction it gets compressed, and then it contracts again. That is sort of a manifestation of a gravitational wave, or the physical manifestation of a gravitational wave. It's called a strain. Okay, so a small change in length per unit of length. Okay, and for this particular black hole merger, okay, we had here on Earth we had a change of this strain, or this delta L over L for given separation of test masses. That was on the order of 10 to minus 21. Okay. One believes that this event happened in a distance of about 10 to the 9, or 10 to the 9 light years, quite some distance, and you'll probably be happy that this doesn't happen in our next neighborhood, because it's a reasonably violent event if 3 solar masses in energy are released in a few milliseconds. Okay, so how to measure that? That sort of is coming closer to the topic of this talk. You basically have to have sort of like an arrangement where you have 3 test masses that are supposed to be in rest. Okay, so no subject of an acceleration or so. So and you just try to measure the distance between these 2 orthogonal directions. Okay, so and that's sort of like a manifestation of this strain. And how can you measure that? You basically measure the round trip time from point A to point B, and compare it to the round trip time from point A to point C, and back again. Okay, so A, B, and C are test masses at rest, which are exposed to this this metric. Okay, and you choose sort of an arrangement that these 2 lengths are the same in quiet times. Okay, so when there's no gravitational waves coming by, then Lx and Ly should be the same. So what you then do is on point A you can send light to B and comes back, and light to point C and comes back, and you compare which light pulse arrives earlier, okay, or later. Okay, and then if it's 0, you see no strain, and if it's different from 0, you do see a strain. That's sort of like the thing you can measure, and from here I start to feel much more comfortable, because I can start talking about things that I actually understand. That would be, how do you measure such a time difference, or how do you measure such a time difference of or equivalently, you try to measure a change of this length of these 2 arms. Okay. So, and probably a large fraction of you have seen this thing before. This is the sort of like the original paper from Michelson and Morley, this Michelson interferometer. I occasionally keep making funny remarks about people using 3D drawings in their papers. Obviously, it's not a recent fad. So this is the original 3D drawing of Michelson and Morley of their interferometer. So they had sort of an arrangement of mirrors on a big granite slab. They were sending light around. This is sort of like the top view. They have a light source sending light in one direction through a half-silvered mirror, and it can take one path or the other path, and you just observe the interference fringes, very much as you have seen probably in the teaching labs. Okay, so funny thing is, they wanted to show that there's, or the purpose of setting this whole thing up was to show that there's something like an ether, and they wanted to measure the speed of an ether. Now, nobody knows what an ether is, fortunately, because that experiment showed that there is no such thing. But at the time, people believed that light needs something like sound or other waves that move into like water that sort of like carry light. Okay. And it would make a difference whether sort of like you move with this medium that carries the light or not. And that experiment was set up to figure out how fast does the Earth move with respect to this ether. And they figured out, okay, if they sort of like measure sort of like a velocity or sort of the length of these two arms when one time in spring, okay, when it sort of like moves with the ether, okay, and one time in fall when it sort of moves against it, they would expect to see a difference in this in their observation, but they didn't find anything, okay, and that was sort of like the conclusion that there is no such thing, okay, so and that was it's really funny because that was one of the starting points of this theory of relativity, okay, so this observation in nature, there is no such thing, so then you need to adjust your mathematics to cater for that. Okay, so it's an observation-based thing, not necessarily someone who sits on the tree and got a big insight. Okay. So again, the microsensor interferometer. I have to admit, this talk was I put it together for some of the outreach activities to JCs, I guess. So probably I can skip now the biggest part. What I want to do now is maybe explain a little bit what these different parts are doing in this interferometer. So you've seen this. I just skipped this. Okay, so you have an electromagnetic wave that has an amplitude and some modulation. Speed of light is constant. Okay, so that I can skip. That's perhaps something you haven't seen all the time. So this is just a normal way of writing down what does a beam splitter do to various amplitudes. Okay, so this half-silvered mirror, we call it beam splitter. What it does is it sort of like has two input ports. Okay, you can send light in from here and here, and two output ports. A field comes out, or wave comes out in this direction and that direction. And it's a so-called linear device. Okay, and the linear device means that you can write down the electric field amplitude here and there as a linear combination of the fields here and there. So and that's sort of like a formal way of writing this down. So the output amplitudes are linear combination of the input amplitudes. Okay, and for a symmetric beam splitter in this particular way. So you have a 1, 1, 1, minus 1 times 1 over square root. Okay, and this minus 1 is sort of like important. Just change this color. Okay, so. It ensures that if you send in light from one side, okay, and nothing from the other side, then both of the C and D ports give you the same amplitudes. Okay, if you would send it in from the other port, you get a minus sign from the other one, and it becomes important if you sort of like come in with two fields A and B, okay, and if they come in with the same amplitude, okay, they add up and all the light comes out on the port C, okay. And in the port D, you have amplitude 1 and minus the same amplitude gives 0. Okay, and if you just flip the phase of the other input, then everything goes out to port D and nothing comes out port C. Okay, so it's just a very simple way of writing down what does a beam splitter do. Okay. You probably have seen all this. I had no idea what sort of like the audience what this is, so I just maybe just like skip to the whole thing. Basically, you can work out what is the field amplitude of a whole Mach-Zehnder, not Mach-Zehnder, a whole Michelson interferometer. It's basically, you have sort of like a phase you pick up in this direction, a phase you pick up in this direction. You work out how to propagate the fields through all of that. And what you end up with an electrical field at the output port here is some amplitude times sine times k of a length difference times some oscillating part. Okay, so that's sort of like the only important result is here that you have a field amplitude that is modulated with a length difference. So you have to see that. The other element we need is how to detect the light. Okay, so usually you don't have something that measures the electric field, but you have something that measures the optical power. Okay, you can look your eye, take your eye, that's the photodetector, or you can put your hand there and see how much warmer does it get when light shines on it. Or you can use a photodetector. All these things measure optical power and not necessarily the electrical field directly. And again, this is something you probably have seen. So you try to work out how much power ends up on a detector with a given area. And you basically end up with an electrical field squared times some constant. Again, the only thing we need is that the detector sees something that's proportional square of this electrical field amplitude at the output. Okay, so and to summarize that, you again have seen this. So the output power coming up from the port of this Michelson interferometer depends on the length difference between these two arms. Okay, in the following way. So it just oscillates with a period that's half the optical wavelength. Okay. Now you can ask yourself, how would you use such a thing to measure a length difference? Okay, which you ultimately want to measure for detecting a strain. And then you try to figure out, okay, I can measure the optical power, okay, and it's not going to be a large change of the length difference. So I probably need to sit somewhere where I get the biggest change of the optical power coming out of it per change of length. Okay, so you try to figure out where is the place with the steepest slope. Okay, that's just here at lambda over 8 displacement, and you just try to keep it sort of like there and watch. Okay, what's going on? Okay, is there anything changing over time? That's a basic idea of this detecting gravitational waves. Okay, and there's the micro version of this. For those of you who haven't seen this in the teaching labs yet, is set up. Now we have here this is our light source. It's a helium neon laser. If you want to come by, just play with it later on. We haven't seen this too many times already. So we have a beam splitter here. This is this gigantic glass cube here. Okay. Then we have two mirrors here. So this is basically these two arms correspond to, go back here, this arm and that arm. Okay, and then we have another few bits and pieces around to make sure we can control the position of these mirrors. We have this green thing here is at the end of it is a photodetector that measures the power. Okay, and that power is sort of like shown on this yellow trace. And you see it wiggles very much like the wiggles here, because what we do here is we vary the length. So we put one of these mirrors on something that moves back and forth all the time. Okay, and that's supposed to be shown on this green trace here. So we put a piezoelectric crystal there. Not we, but my team here put this together. So there's a piezoelectric crystal, and you apply a voltage to it, so it gets thicker and thinner all the time. Okay, and the voltage we apply to it is shown in this green trace, and the outcome of this photodetector is shown in the yellow trace. So it oscillates between low light and high light. Okay, and if I just change what can I change here? The amplitude of this green green voltage, basically the voltage on this piezo crystal, then you see these patterns become so this amplitude gets much larger, and these oscillations become much denser. Okay, so that gives you an idea that this really changes the amplitude of this oscillation. If I place my hand in there, okay, I see a constant optical power. If I place my hand in there, I also see a constant optical power. So this sort of like gives you an idea that this is really an interferometer that works as advertised. So each, you can convince yourself. Just never trust me. Just try it out yourself. So what do we learn from this? Now we learned that sort of like between sort of like a full oscillation of this this yellow pattern, the position of this mirror has changed by half a wavelength. Okay, this is according to this mathematics here. Okay, so we're able here. This laser works at 632 nanometers. So from one wiggle to the other wiggle, we have a change of about 300 nanometers of the position of this mirror. Okay, so that's not all that much, and you see that it wiggles a little bit different if I talk. Okay, I don't know if I just make this smaller. Then you can see as soon as I start talking, the whole thing shakes a little bit because these mirrors shake. Okay. Now what you can do is try to not wiggle the mirror, okay, and keep it sort of halfway stable on one point, and then just measure the optical output and try to figure out how much has this mirror moved. Okay, we cannot like quickly demonstrate this here, but so if we just do a rough estimation how accurate that can be, is maybe we can measure the output power, sort of the relative change with about 1%. Okay, this oscilloscope maybe has 200 points vertical, so let's say we can do 1% accuracy with this readout. Wavelength is 632 nanometers because of a helium neon laser. And if you just take the slope of this response and the length of 30 centimeters perhaps, then we get a certain length sensitivity of about 1 nanometer. So that's already quite sensitive. And the corresponding strain, if you divide this length by the length of this arm, about 3 times 10 to minus 9. Okay? So already not so bad. However, we are far away from seeing any gravitation wave. At least for these type of black hole mergers that led to this event. So in order to see that, with a significantly high signal-to-noise ratio that you can actually claim to have seen something, you need to make this whole instrument 13 to 14 orders of magnitude more sensitive. Okay, and that's sort of like the beautiful work these people have accomplished, or this huge team of people they have accomplished. Okay, so the question is how can you this is where you start thinking as a physicist, okay, an experimental physicist. You tell the engineer, can you make this 13 orders of magnitude better? They'd probably say no. They're happy when they see like 10% better, 20% better, maybe factor 10 better or something. 13 orders of magnitude is hard. Okay, so so you need to start. Okay, fill this together. What does determine this strain uncertainty? Okay, so just write down this delta of the strain you want to see. You work out what does contribute to that. One is the arm length. Okay, if you make the arm length larger, okay, your uncertainty goes down. Okay, if you make your interferometer more responsive, and this is sort of like this is basically the output power versus divided by input power change per unit of length. That's basically the slope I showed you before. Then it depends on the optical power you use to observe that, and the uncertainty with which you can measure power. Okay. So these 4 things you have to play with, and you need to find 14 orders of magnitude or 13 orders of magnitude. Okay. So you can increase the arm length. You can increase the interferometer responsiveness. You can increase the input power. Here we work with maybe milliwatts or something like that. You can decrease the sensitivity over which you have in measuring the output power. And these guys did all of that. Okay, so but what you really have to do is here you see me. If I talk, the whole thing shakes because the mirror shakes, and we know it shakes perhaps by 10 nanometers or something like that. The type of length change you want to observe there is much smaller. So you need to also make sure that your environment doesn't disturb such a measurement. Okay, so length, that's sort of the easy part. Go from 0.3 meters to 4 kilometers, okay? The US is a large country, so space is not a problem. So they basically, this is a larger version of this thing here. They took a 4 kilometer long arm. It gives you four orders of magnitude. This is not so bad, okay? They have a long vacuum tube because you don't want to have any effects of air going on. Yeah, and that sort of helps you already a lot. Okay, so of course you could say, why stop at 4 kilometers? Okay, think big. The other suggestion that has been around for quite some time is use a bunch of satellites. Okay, you can have an orbit of an arrangement of satellites that sort of like keep that sort of follow the Earth. Okay, and have a relative spacing that's sort of fixed. And you can have them apart about 10 to the 6 kilometers. Okay, that's a lot. Then you would gain immediate. So with one idea, okay, you get 9 to 10 orders of magnitude. Okay, so that brings you much closer to that from this simple setup. Okay. For the longest time ever, I mean, both attempts were tried. Okay, so and that may even be built in a not too distant future, because they now saw these gravitational waves and said, hey, maybe it's worth looking at that. The problem we have with these really long distances is you saw this gravitational wave feature happen basically within a few milliseconds. Okay, and your basically you need to have, it's like a microphone. Okay, so it's basically the audible frequency. And the resolution with which you can resolve these gravitational waves or these oscillations need to be captured by a microphone. Now this particular interferometer basically takes a certain time to measure a strain distance. Okay, if you work out what is the time it takes for light to be sent out from one end and return back, then somebody who has a calculator can sort of try this out. 10 to the 6 kilometers, 10 to 9 meters. When I tried to hack it into my calculator, I got something like 6 point something second. Okay, the light from here and back again. You're not going to see these very violent events because they happen on a millisecond time scale. Okay, so that's a great interferometer. You get a lot of gain in this strain sensitivity, but you won't see very fast events. Okay, plus it's also not so cheap to send 3 satellites around, but that's a different story. Okay, so next idea you can try is push the responsiveness of your interferometer. So, or you just how much information do you get per path travel? So even Michaels and Morley back then had granite slab that was, I don't know, a few meters, I guess, in size, and they wanted to be more sensitive, so they recycled sort of part of the distance they had by putting a few mirrors and basically reflecting light back and forth a few times. If you try this a few times, then at some point the problem you run into is at that time they had silver mirrors, I guess, and that still for visible light, or this green light, has a reflectivity of about 90%. Okay, you do this a few times and you lose a lot of light very quickly. Okay, so gold is a little bit better at infrared wavelengths, so you can do this more often, but it's also still not a good idea. So if you want to sort of like recycle the space you have for many passes by using mirrors, you need to improve mirrors, and that's sort of like a development that has been around for the last few decades or so, and you don't use metal mirrors anymore for very high reflectivities, at least in the visible optical range, but you use an arrangement of dielectric films of different refractive index. Okay, so this is like many of the fancy mirrors, maybe even these mirrors. Yeah, these are not silver mirrors anymore. They're dielectric mirrors, and they make them sort of like a high refractive index, low refractive index material, and they stack them on top of each other, such that a reflection from the optical thick to optical thin, where you get a phase shift here, okay, and a reflection from this interface interfere constructively. Okay, so it's yet another interference game, and if you have sort of a stack of these layers, each quarter wavelength thick, okay, maybe around 20 or so double sandwiches, then you get very quickly into this regime where you have reflectivities of 99 point blah 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 %. So you can make incredibly good mirrors with these dielectric coatings, and the reason for that is these materials are ridiculously transparent. Okay, metal, you always absorb some of the light. Okay, so you cannot push this much further. Okay, but these dielectric coatings, they have very low losses. So you can make, these days mirrors probably up to 5 nines or 6 nines or something like that. If you know how to make them really transparent, but that's how most of these mirrors work. I think realistically you can have maybe 10 to the 3 to 10 to the 4 round trips in such mirrors, and that is actually one of the end mirrors they used in this LIGO telescope. So it's about head of a person, that size, sitting on a silica substrate. The whole thing weighs about 40 kilograms, and you see this sort of greenish reflection. It's not because they were using green light, but this mirror was actually designed for 1064 nanometers. That's the light they were using, but it's also reflecting a little bit in the green, so that's sort of half the wavelength. Because if you have, this is you get constructive interference for one wavelength, then half the wavelength will also be constructive. Okay, so basically dielectric mirrors were really part of this whole trick, and the mirrors there actually were made in Australia. So it was a very international collaboration. Okay, so how can you use such mirrors to enhance the sensitivity of your interferometer? What you basically do is you try to take 2 of these mirrors, and we don't have it here, but if you at some point come to our labs, you would find probably a device like that. We have 2 mirrors with the same reflectivities, and so same reflectivity means 1 minus a tiny little bit. Okay, so the rest, most of it gets reflected, but a tiny little bit gets through, and the losses are sort of like negligible. So then you can sort of like work out how much power do you get through this whole arrangement as a function of the distance. And I'm not going to bore you with the mathematics, because it's again adding amplitudes and making sure that you got a consistent solution. But what you get is you have an output power that for certain spacing of these mirror coatings, you manage to get all the light through this thing. Okay, and it very quickly decays if you displace the mirrors a little bit from this resonance condition. And you hardly get any light through, and then again it gets a very high transmission half a wavelength later. Okay, so this calculation is shown here for a reflectivity of a mirror of 97%. You can make this much better, but what you already see here, compared to the sinusoidal oscillation in the Michelson interferometer, yeah, this has a much steeper slope. Okay. And that's what I mean by increasing the sensitivity of this interferometer. Okay, so you just by using smart coatings, or a smart way of converting a length into an amplitude signal, you can gain a lot more sensitivity in the position of this device. It usually means if we try to build up such an interferometer just on these poles like we did here, you won't see it working. Okay, because it shakes too much. You need to make this much more sturdy, so you only have a wiggling of a few nanometers perhaps, or even less. Okay, what else there is? Okay, so again, more mathematics, but what you can work out is sort of like this slope that tells you how much change in power do you get per length change, and you can sort of like compare the numeric values of the Michelson interferometer where this relative output power change per length change in the steepest slope is say 2 pi over lambda. This is work this out. It's just mathematics, okay? And for these Fabry-Peyro resonators, it's the same factor times 1 over 1 minus reflectivity. So if your reflectivity is close to 1, then 1 minus something close to 1 is very small, and it's in the denominator. So this factor here can get very large. Okay, so that's sort of like the other idea. You need to increase that. You can easily bring this to a factor of 100 or so. Okay? 100 or 1,000 is possible. Gives you 3 orders of magnitude in sensitivity. Okay? So you have to collect bits and pieces to get these 13 or 14 orders of magnitude. Okay, you need a bit of a trick to convert this sensitivity of these cavities or optical cavities into something you can use in a Michelson interferometer. Remember, for detecting this strain, you need to measure length distance between this direction and that direction. Okay, and this resonator only measures a change in one direction. So you need both. And the way is, what you do is basically you think of what does such a resonator do compared to a normal mirror. And you can work out, okay, if you compare the field that comes back, okay, or the ratio of the field that comes back to the field that comes in, you basically see that the output power is the power is the same for a good mirror, but there's a phase shift. Okay, it's just how you describe what does a mirror do if you move it away a little bit. And you can do the same thing for this Fabry-Peyro. If you have here very high reflectivity and here less than 100%, then all the power you send in will come back. So that's the same. But there's a change of this phase as a function of this displacement of the second mirror. And again, it's mathematics. You can work this out. This is sort of like the graph that showcases you what the result of this is. So I plotted this change of the phase as a function of the phase change of the mirror. So this would basically be the if you look at that red trace, that would be the trace corresponding to an input mirror that has a reflectivity of 0%. Okay, so basically it's not there. So all the light goes through. So the red line would be just a naked mirror on the end and no mirror in the front. Okay. Now I slowly increase the reflectivity of the first mirror. Okay, and you see this slope gets steeper and steeper and steeper at a particular position. And for 99%, you see for a long time no phase change, and just near the resonance you have a very steep change of this phase, okay, and then it sort of gets quiet again. And this is basically what you're trying to use. So again, lots of mathematics, you can work this out, but the phase change of the reflected light as a function of the effective phase change of the backside mirror gets sort of amplified by another factor which has a 1 minus reflectivity in the denominator. Okay? So by having this reflectivity of the first mirror being close to 1 or 99%, okay, you would boost this up by a factor of, in this case, 400. Okay? So that's sort of that's nice. Okay, so you can this helps. Okay, 2 orders of magnitude at least, or maybe 3 orders of magnitude. Okay, so and you see, I mean, if you gain a few orders of magnitude for each of these terms, then you eventually get there. Okay, so this is how the device actually looks like, at least in principle. So you have these 2 cavities. Okay, each of them act as a sort of like a super mirror with this amplification of the sensitivity for this length change here and there, and you have again a Michelson interferometer. Okay, and all you do is you look at the output power, as a function of the input power, and see do you see a change of the output power while these mirrors wiggle a little bit. Okay, so the idea is you have sort of like here maybe a few orders of magnitude, then another few orders of magnitude by length. Okay. And yeah, okay, so then there's a subtle trick they discovered. I mean, the people have been working on this instrument for decades. Okay, so it's not yesterday's news. But one trick they discovered reasonably late in this game is where do you choose how to operate this interferometer? Okay, naively you would say, okay, you measure this output power. Okay, you see the output power versus the phase shift. Okay, you would like to sit somewhere here because it's the steepest slope. Sounds reasonable, but it turns out a much smarter way to operate that is you try to look for, and this is phase sensitivity. Basically, the slope of this curve is shown here, the blue one. Okay, it's largest at that point. Okay, or at that slope, it gets a negative slope, and that's what you want to see. But if you try to figure out what's the phase sensitivity per output power, okay, basically have to divide the blue curve by the red curve. Okay, and then you see. You basically this curve dies out linearly, okay, near zero, and this dies out quadratically, okay. So and that means that this phase sensitivity near almost zero output power is the largest, okay, the output power. And that gives you another, maybe 1 or 2 orders of magnitude. You can sort of like try to be very close. To sort of like a dark fringe. You don't look at half the intensity fringe, but try to sit very close to the dark fringe, okay? And then you get very, very sensitive, very high sensitivity of the of this length change per output power change. So that's it's a very simple trick, okay? They figured it out rather late in that game. They had all kind of funny ideas, and I said, this works out. And what you need to do then is you just use lots of input power, okay? Send a lot of power in, make sure you arrange that very little power is coming out of that thing, okay? And most of the power is reflected back. And it's sort of like they have another mirror that sort of recycles that power, okay? So you have a moderate laser there, and then you have a lot of power circulating in the whole thing, and a very tiny little power, a milliwatt probably only, coming out of this whole thing. Okay, and that these steps add up, 3 or 4 orders of magnitude for each step, and that actually brings you from this flimsy Michelson interferometer to some of these LIGO detectors that have enough sensitivity. Light detection itself is they were looking at very fancy ways of measuring light very accurately, but you're basically limited by the shot noise of light. Okay, so and that's not so much different from this photo detector than from what they are using here. Okay, the basic idea is you convert each photon into an electron and measure the charge. Okay? And you're basically given limited by the shot noise of this charge measurement, or the shot noise of this photon noise correspondingly. And there's not much you can do, and you very, very quickly reach into this regime without doing a major effort. It's a very simple relationship between the current of a photodiode being detected when a certain optical power shines in, if you know the wavelength. So you're going to sit down at some point and work this out. And it's a very simple relationship, and it holds very easily for that detector we have. Okay, the noise you see in this, or this uncertainty you have in this power measurement, is essentially proportional to the square root of the number of photoelectrons or photons you have seen. So the trick to get a relative measurement of output power, or uncertainty in output power, to total output power is to increase the power you measure. But that turned out not to be a severe limitation in this whole measurement technique. So optical power you can measure very accurately. At some point you're just limited by this shot noise of the photon stream that comes in. Okay, so this is sort of the device they put together with a few numbers. So you have a laser source of about 20 watt. If you go into one of these research labs here, I mean, people boast much more powerful lasers. So there's a 20 watt infrared laser. Then 4 kilometers of interferometer arm length. You need to have the space for doing this. They have very, very fancy mirrors. Okay, in a sense that's sort of like the recycling cycling power in these resonators is about 100 kilowatt. Okay, and And that's a combination of the effect of this resonator, light bouncing back and forth, and this Pauli recycling mirror, where they look at a few milliwatt coming out here, and all the rest is sort of like sent back to this mirror and fed back into this interferometer. So that's really all the setup. There's a very simple Michelson interferometer, okay, with slightly macroscopic dimensions, and a very fancy mirror system, admittedly, and sort of like the uncertainty that they have shown is plotted here as a strain noise. Okay? So the reason why this is sort of like an important measure is to figure out how much energy is there per frequency band due to noise. So it basically characterizes their uncertainty, how well can they detect or distinguish an external event or a gravitational wave event from just noise in the system or measurement uncertainty. Okay, and that's sort of like a noise spectrum you see. They see a lot of, what this graph shows is the traces from these two interferometers, a few thousand kilometers apart. So they see a funny resonances at very discrete frequencies, which is looks very horrible, but it's actually not a big problem because these perturbations show up at very specific frequencies. So you can be sure that if you see something like that, it's a systematic problem, and you just don't listen to this particular tone. Then a bigger problem is you see an increase of noise for high frequencies. That's the shot noise of the photodetector. That's sort of like hard to overcome, or just limited by the amount of power you can dump in your system. And then sort of like for low frequencies, you see what they call a seismic wall. Okay, and that's a problem I haven't so far talked about. Okay, and that's related to the fact that you cannot. You can push your sensitivity of your instrument more and more, but eventually you see environmental noise. Okay, so here in this flimsy Michelson interferometer, if I start talking towards one of these mirrors, you see the whole thing shakes already. Okay, it shakes a few 10 nanometers. Now, if you work out, you want to detect a strain of say 10 to minus 21, and you have a length of 4 kilometers. 4 kilometers is 4,000 meters. Okay. Say 10 to the 3 meters because it's easier to calculate, times 10 to the minus 21 is 10 to the minus 17 meters, okay, something like that. Maybe about an order of magnitude wrong, or 2, okay. It's still very, very small, okay. So they have an uncertainty or a noise of this position of these test masses of 10 to the 17 meters. Okay, that's not a lot. So what's a typical size of an atom? 10 to minus 10 meters or so. Okay, still 7 orders of magnitude missing, maybe 8. So nucleus gives you another 3 orders of magnitude. So they measure this test mass position with an accuracy of 10 to the minus 7 atom diameters or something like that. Okay. First of all, you ask yourself, okay, how is that possible? Because the mirror itself is certainly not smooth enough that you can define. Say the mirror starts here and air starts there. Just because it's made out of atoms, but you can very well define an average position, okay? Because you average, this line is averaging over many atoms, okay? And you can very well define an average position of all these ensemble of atoms. The number is large enough that you can easily make up for these 7 orders. But that's sort of like not the main problem. The main problem is that this test mass needs to be addressed. Not being shaken around by acoustic noise and seismic noise. So one of the big challenges they had to face is to make sure that this interferometer is very well isolated against the environment. One of the tricks they did, they put the parts in these vacuum tubes, so you have basically no acoustics around there, or not even gas molecules bumping into the mirrors. But still, you need to hold these mirrors in place. I mean, you cannot, say to the mirror, stay in space and walk away if this falls down. So you need to hold it somehow, and if you hold this mirror, it still shakes. I mean, you sit in an office and a truck drives by outside. You feel the shakes of the truck. And they went into an area where there are not many trucks running by, but still you have seismic noise. Okay. In some experiments, you see even if a river is close by and then the water sort of like makes noise, and you see the seismic noise. So they needed to have a way of getting rid of all these vibrations down to the level of 10 to the minus 7 or 10 to the minus 17 meters. Okay, that's it's not a lot. Okay, so it needs to be really sitting well in the place, and the way they did this is a remarkable simple idea. Okay, so this is sort of this contraption they use. This is sort of like the what they call the test mass. Okay, so part of these resonator mirrors, and it's suspended with glass fibers from another test mass. It's suspended with steel wires from another mass, and steel wires another mass. Basically, it's a chain of pendulums. Okay. Plus another chain but we'll come to this later. Okay. So and this is probably something you've seen in advertisement for classical mechanics course. Okay. So but here's maybe this is a new demo thing here. If you have a pendulum, okay, and you want to make sure that this is my test mass, okay, and the test mass should be at rest, okay. Now you want to isolate this against vibration of the Earth. Now if sort of like the Earth moves at low frequencies, the test mass moves also with low frequencies. And then at some point there will be a resonance frequency, and you see this. I shake it a little bit, okay, and it oscillates with larger frequency. That's maybe somewhere here. And if you have very high frequencies, okay, then the Earth shakes a lot, and this thing moves very little. Okay, that's basically this curve here. And for a simple pendulum, you find that if you're way above the resonance, then this sort of responsiveness of the wiggle below to the wiggle above goes with 1 over omega squared. Okay, and that helps a lot because you can easily get 2 orders of magnitude. Reduction of wiggle by going a factor of 10 higher, okay, and you don't stop at one pendulum, okay. You just make a whole chain of these guys. Each one buys you 1 over omega squared for high frequencies, okay. So and that's what they did. And they had a few pendulums, okay, with resonance frequencies, something totally normal. And they above 10 hertz or something like that, they're above the resonance frequency, and you see all the seismic noise dies out with omega to the minus 8. Okay, so 1 order of magnitude in the frequency brings you down 8 orders of magnitude in wiggle. Okay, so this is the trick. Factor of 100 in frequencies brings you down 16 orders of magnitude from Earth wiggling influences, and that's really how it works. So. Very simple physics, okay. Very effective way to get down 16 orders of magnitude with some silly noise. It's not all that simple, but that's the main idea of this damping system. And you find companies that offer you very fancy damping systems. They have one fancy damping system here that brings, I think, the basic wiggle is a few micrometers or less than that. But pendulum can do wonders and damp out noise very, very efficiently. Downside is you need to, if you have decoupled, what this thing down there does from the outside world so well, you eventually need to position this mirror also at a well-defined place. Now, the problem is if you have cannot just move this back and forth to compensate for that position. You need to have a smart way of moving this mirror finally to the exact resonance condition. And the way they do it is they basically have a second pendulum chain, and made up from the same type of masses. They basically have just magnetic coils between these two to adjust these masses with respect to each other. Okay, just by forces, just a magnetic force between these two masses. and then they can displace these mirrors without being influenced by the shakes from the outside world. Okay? At the very last stage, they don't use magnetic coils anymore. They just have metallized these mirrors and use electrostatic forces to have an attraction between these two mirrors. And that's how they can displace the mirror exactly in resonance frequency. They also need to compensate. It's kind of a funny tidbit. This laser beam, the 100 kilowatt is kind of a lot of power, and it exerts enough force on the mirror, just because that sort of laser beam needs to turn around. Okay, that leaves a certain momentum in this, or like a force in this mirror, and displaces it. So they need to compensate for that.
So it does not heat. It does not heat the mirror.
Of course, yeah, it heats the mirror.
Before and so on. So
apparently, they got this under control. Of course, it heats, but 100 kilowatt is a lot of circulating power.
Yes. So it does not damage the mirror.
Yeah.
The quality of the software, I don't know.
Yeah, obviously it does. Maybe they have damaged a lot of mirrors. Chances are they had. The trick is to make mirrors with extremely low losses. So the power you deposit in these mirrors is very little, so they don't warm up, or these coatings don't get spoiled. And that was, it's a masterpiece to make such a mirror. Okay, it's not don't go to your evaporator and make such a mirror. Again, it's a decades-long research to make these coatings really good. Yeah, that's it. Okay, so that's basically the key physics ideas. How to make an interferometer very, very, very sensitive. Okay, so you need to reduce environmental noise. You need to increase the sensitivity. You have a product of 4 or 5 terms that contribute to the sensitivity of your Michelson interferometer, and you try to get 4 orders of magnitude out of each of these things, and try to push hard. And eventually you're down at a noise level. You can measure extremely low, very little displacements or the strain that is eventually just induced by these black hole merger events. And that was sort of like the first result they have seen. So this is like a very strong. This trace here is sort of like the measured displacement, basically after they measured the photocurrent and convert it into a strain. That trace below, without the noise, is a theory simulation where they were using these 2 test masses and run a model calculation how the gravitational wave would look like. So there's a very good overlap between the theory and the observation, and that makes them conclude that this is actually what happened. This black hole merger. So this is sort of like the frequency spectrum. I don't have a trace, but this is sort of like a short blip, and in the audible frequency range. So this goes, it starts at low frequencies and gives a high pitch, and then the whole thing is over in a few milliseconds. It goes in whoop or something like that, and then here go your 2 black holes into one. That was not the only result they have seen, or the only observation they had. Shortly after that, they found a second candidate, and they're sure that this is sort of like confirmed. Again, this whole interferometer was not really running into observation mode. It was a test mode. Okay, so they were still testing the whole setup, and but they were sensitive enough to catch this event. That's the second event. A few months later, we had higher frequency of the event, and again, they saw a strong correlation between the observation of 2 observatories at a few thousand kilometers apart. So that's sort of like the second candidate they have identified. This is not such a clear trace, so you need to work out exactly what is the signal-to-noise ratio, what's sort of the confidence you can have into the observed model being a black hole merger, and again they believe that this has been one. And they always show these spectral traces. I don't know how this sounds like, but giving from looking at the number of wiggles, you see more wiggles here, so that this event maybe took a bit longer until the black holes emerge. But that was sort of like the second event they have observed so far. Now, maybe to show you, that, apart from these interferometers with the Earth-based Michelson interferometers, what else can be expected? So this sort of like LIGO interferometer that has detected these two events can detect events. So this is sort of like a map I stole from this website. So these traces here, this LIGO was what was used to see it. That can detect black hole binaries merging basically. That's what the event they saw. Okay, so this purple trace is the instrument at its current sensitivity. They have already a few plans how to improve things even more in terms of like sensitivity, and the upgrade of this system will allow them to see sort of like much more conveniently neutron star binaries or neutron stars themselves. I mean, they rotate and they also emit gravitational waves. So they would see many more events with this upgrade on a time scale of a few milliseconds. Okay, so that's sort of like the time scale. Now, with all this enthusiasm about gravitational waves, this space-based interferometer got a bit of a revival as well, and so people think maybe they should sort of like start this satellite-bound interferometer again. Due to the larger distance, you would be sensitive to events that happen on a few minute time scale. I hope I remember this correctly. So one of the events they hope to see is the supermassive black hole binaries. Apparently such things exist. Okay. They make a lot of waves. I don't know what the other acronyms were, okay. But there are many more galactic events that that would leave a trace in this gravitational wave pattern on a different time scale. Okay. At some point, there are binary star. I mean, whenever you have a binary star system and they sort of move around, you always get gravitational waves, and there's lots of binary stars around, so that will give you a relatively huge background. There's one thing that was actually it's kind of funny. They used for the first indirect evidence for gravitational waves, and that was not an interferometer where they measured the strain, but they measured the energy loss of a star due to gravitational waves. Okay, and the way they did this is there's some neutron stars, I guess, that act as radio transmitters. They send out because they sort of like have a well-defined magnetization, and they basically send out radio clips. Okay, you can sort of like put out an antenna and listen to these pulsars. Okay, and they have a very precise timing. Okay. So at some point they started to look at this timing. It comes with a few milliseconds or so. That it's very fast stars. So some are slow, some are fast. And they started to compare the spacing of this signal you see here on Earth compared to atomic clocks. Okay, one can build better and better clocks. So by measuring the change of this periodic pattern you receive from these stars over time, you can sort of like infer how much energy are these things using. Okay? And it follows a particular pattern that's compatible with what you would expect of energy loss due to gravitational wave radiation. And that's sort of like these detecting schemes they're also setting up here. But that happens on a much longer time scale because you need to see, okay, how much energy has that thing lost, okay? And it takes a while to build up that timing difference, about maybe 10 years or a few years time difference. You need to measure this thing going slower to make a sensible statement about gravitational waves. Yeah, that's I guess that was basically it.